Hello, my name is Liraj Chaudhary, and I will be presenting my hybridization project. My molecule is SiO2, or silicon dioxide. The central atom of silicon dioxide is silicon. This is necessary to jot down because we will be finding the condensed electron configuration of the central atom, or silicon. To do this, it is relatively easy. We've got our desired element, which is silicon, and then we go to the row before it. So we are in row 3 right now, which is this row. But we will go to the row before it, so row 2, which is the row I have highlighted. And then we would find the noble gas, which is neon in this situation, and we would jot that down. The reason for this is because neon is a placeholder for all of the orbitals that have been filled until it. Basically, it summarizes the electron configuration up to that point. Now moving on, right here, these two rows, these two columns are the S columns. This is very necessary to note because we are 1 in the 3rd row and 2 we are in the S columns. As such, we are in the 3 S's right now. We can jot that down. We know that we have to pass these two elements to reach silicon, because silicon is on the other side of the periodic paper. As such, we know 3s will have a superscript of 2, and it has a max superscript of 2 because it is an s orbital, and s orbitals only have 1 orbital, and each orbital only has 2 electrons. Moving on, we go over to the p section, which is right here, and we are in the 3rd row, so we are touching 3p right now. Let us shut that down, 3p. And then we have aluminum here, which we have to pass, and then we touch silicon. As such, our superscript would be 2, and this is our final condensed electron configuration. Moving on to the condensed energy diagram. We have our y-axis, which represents our energy, and our x-axis, which represents the types of orbitals. We currently have the s orbital and the p orbital. Neon will go into the s orbital. We'll go into the s orbital. So neon goes there. Above that is a horizontal line, which is 3s. And then since 3p has more energy than 3s, it will be above 3s. It'll be right here, and there are 3 orbitals because there are 3 horizontal lines because there are 3 orbitals in 3p, and there is 1 orbital on 3s. There's 1 line, horizontal line in 3s because there is 1 orbital in 3s. Now, if you were to look here, there are 2 electrons in the 3s. As such, we'll put 1 facing up and 1 facing down, which fills in 3s. And if you look at 3p, there is also 2 electrons. However, if we were to follow Hund's rule, every single orbital gets 1 electron before you can pair them up. I would like to move on to hybridization. However, we need to find out how many things surround our central atom, and we cannot do this without a Lewis dot diagram. As such, we need to draw the Lewis dot diagram. So we have our central atom, which is silicon, and then we have our surrounding atoms, which are our oxygens. The oxygens should be an equal distance apart from the silicon. Then we use our need-have method. Silicon needs 8 electrons, and oxygen needs 8 as well, and there are 2 oxygens. As such, there's 24 electrons needed in this whole molecule. We have 4 from silicon and 6 from oxygen. This is shown if you go to the periodic table, where carbon is has 4 electrons, or silicon has 4 electrons, oxygen has 6. As such, oxygen needs 2 valence electrons, and silicon needs 4. So we have 4 from silicon, and we have 6 from oxygen. However, there are 2 oxygens. As such, 6 times 6 is 12, plus 4 is 16. 24 minus 16 gives you 8. Each bond can have 2 electrons. 8 electrons divided by 2 gives us 4. We can have a total of 4 bonds. Each oxygen gets 2 bonds and 2 lone pairs. As such, this is our final Lewis dot diagram. After completing the Lewis dot diagram, we can move on to hybridization finally. Hybridization. If we look at the Lewis dot diagram, we have two things that surround our silicon, which are two double bonds. Double bonds are truly treated as a sigma bond during hybridization. As such, we have two sigma bonds. Hybridization lets the central atom create new hybrid orbitals in which orbitals at the same energy level are averaged out. In this scenario, we would be creating a hybrid of 3s and 3p. We would draw two horizontal lines to represent the two sigma bonds. They'd be drawn in the middle of each of those orbitals. So right around here, they're drawn just in between 3s and 3p. And as we know, each sigma bond gets one electron which faces upwards. Which faces upwards. Now, to name it, we would look at the energy level it comes from. So it comes from 3. So we start off with 3. And then we would look at how many sigma bonds we have, or how many bonds we have in total. And we have two sigma bonds. S can have a total of 1 orbital. P can have a total of 3. One sigma bond marks off S, and one sigma bond marks off P. As such, we get 1s1, 3s1, P1. However, we get rid of the 1s because they are not needed. And this would be the name of our hybrid orbitals. However, we are not done yet. Rather, we have a lot of work to do. If we look back at our Lewis dot diagram, we would realize that we have double bonds. And during hybridization, we actually need to include those. We need to tell everyone that we have double bonds. As such, we would draw two more orbitals underneath each, two separate orbitals to the right of a dotted line to show that we have pi bonds. So we would write pi under each horizontal line. And then we would draw one electron for each of them. And this is our final draft. Now that we are done hybridization, we can move on to intramolecular forces. However, to do that, we need to realize that we need the electronegativities of the elements in our molecule. We have silicone and oxygen. Oxygen's electronegativity is 3.5, silicone's is 1.8. 3.5 minus 1.8 gives us 1.7. That is the electronegativity of this molecule. And electronegativities between 0.5 and 1.7 are always going to be polar covalent. However, you would think that silicon dioxide is polar covalent, right? But you're wrong. Because if you look at the structure here, the diagram, the Lewis dot diagram here, you would realize that 1, the molecule is linear, and 2, it is symmetrical. Every single symmetrical molecule is non-polar covalent. As such, silicon dioxide is non-polar covalent. However, I'd like to add that there's a second way to draw silicon dioxide. You have your silicon in the middle and then 4 oxygens surrounding it. And then a chain is created, just like this. And so on and so forth. Now, this is very intriguing because the second shape determines the silicon dioxide's physical properties. There are numerous there are covalent bonds here, which are extremely strong, and when silicon dioxides come together, they create a lattice type structure, or a covalent network, which is one of the strongest structures one can get. As such, this compound or this molecule has a great boiling point and a great melting point. In fact, it is odorless. However, the melting point is 1700 Celsius, and the boiling point is 2300 Celsius. As such, we can realize that silicon dioxide is a very intriguing molecule with covalent bonds that stick together. However, I'd like to leave you off with that, and I hope you learned something about Lewis dot diagrams or hybridization, or you found this presentation intriguing.